Hey, hello. Hi, everyone. This is Research Jam number 8. We do Research Jams every 8 or 9 weeks. So that means it's almost a year and a half that we've been doing this. So it's quite easy format. People show up and present what they're working on. A lot of papers have come out of Research Jams. So usually after the presentation or in preparation of a presentation, they will make a little push of the project. It's a nice momentum will be generated and usually papers come out of it. So no guarantee, but that's just the pattern we've been observing. So today we have 5 speakers telling us about their projects. One of them actually has 3 projects to talk about. So I was trying to convince him that try to go faster. We only have 10 minutes, but let's see how it goes. So anything else?
I guess, Roseanne, if you intro people, I can do the timing. And so I'll be the jerk that'll write like 30 seconds on the screen if you have 30 seconds left. So speakers will have 10 minutes. So at 9 minutes 30, I'll write like 30 seconds on the screen.
Right. So every speaker will have 10 minutes. If we have time, we can do Q&A, but we can leave the bulk of Q&A on our Discord, which is a server that you go on. There's a voice channel. You join. It's kind of like a voice hangout. You can ask the speaker questions. So afterwards, the latter half an hour of this meeting will be spent there. For those who are watching this on YouTube, I'm speaking to the future you. Next time, try joining live because we'll do a little unrecorded part in the beginning. It's quite fun. Cool. Let's get started. So the first one is Charles. If you're here. Hello.
Okay, great. Thanks. Thanks for having me.
It's Charles, like number of third times or fourth time.
Third, thank you. Yes, well, I appreciate you guys doing this. You know, I work totally by I'm totally self-funded, so this is a great opportunity to show these things off. And also, I do work sort of in the sort of on the outskirts of this field because I come from a background in theoretical physics. So I appreciate just having the feedback. And also the timing now. You guys changed the time of this. Before it was pretty good, but then you kind of moved it around. I had client meetings on Thursday, so I couldn't come. So I appreciate doing this. Let me get started. What I want to talk about today is some theoretical work I've been doing. Again, I've been doing this with Michael Mahoney and another fellow, actually an old friend of mine, who's a theoretical physicist, Mirko Mintarelli at Microsoft, on deriving using some techniques from statistical mechanics to derive our weightwatcher alpha hat metric. Now, I've presented the weightwatcher alpha metric here before, but I'll just do a quick review. Weightwatcher is an open source diagnostic tool for analyzing deep neural networks. It lets you, for example, can help you when you're trying to train very large models. It can help you learn how to train them. We've been able to show that we can predict trends in the generalization accuracy of a very large number of state-of-the-art production models, both in the computer vision and natural language processing domain. So our alpha hat metric has been shown to correlate remarkably well with the test accuracy across various kinds of models. Here's an example of looking at VGG11 to VGG19, and you can see that our metric tracks very well the test accuracy, and we were able to do this across hundreds of models, and this work has actually recently been published in Nature. So today I want to talk about the theoretical reasons for why this works. We've never really talked about why, and I've been trying to formulate. The ideas come from theoretical physics, and I'm going to try to formulate them in a way that would be helpful to the machine learning and deep learning community. So the idea here is that there's an old model in the statistical mechanics of learning, or sometimes called the statistical mechanics of generalization, called the student-teacher model. It's in a very classic book by Indel and Vanderbroek, although I don't think they're the ones who developed it completely, because it comes back from the early 90s. And the idea is to try to model the generalization error of a perceptron as a model for a multi-feed forward network. And this is something which is really an alternative to VC theory. It's a very different kind of theory that was popular when I was young. And I'm going to show how you can use this theory with some modern extensions to derive an expression for the generalization accuracy of a general purpose deep neural network. So the idea in the classic student-teacher model is that you would assume you have some Gaussian data, just random IID Gaussian data. And you're going to feed it into two different networks. You have a teacher network T and a student network J. For historical reasons, it's called J. I don't know why, maybe it's German or something. But and the idea, each of them produces a label. And in a simple perceptron, it's just J dot. There's some weight vector dot the data, and you get a label. And there's a sign, and you take either the positive or negative depending on the sign function. So the sign is sort of like in what we would call modern activation function, and you get a label, plus or minus 1. And the idea is you know the teacher, and if you want to figure out how accurate can the teacher be, or what kind of error would the teacher make, you ask, well, let's consider all possible students that might look like the teacher, and let's integrate over all the possible students that we could dream up that would try to emulate the teacher, and let's measure the error between the students and the teacher, and that would give us some idea of the student teacher error. And then we average over all the data. So you average over all the data and you average over all the students, and that will give you an estimate of the error. And this actually works remarkably well for perceptrons. This has been shown to, in very, very toy models, this works. There's a relationship to the theory of disordered systems in statistical physics, is that when you average over the data, it acts as a kind of quench disorder. And when you have these various learning parameters, the hyperparameters, it looks like an optimization problem in physics. And so what we're going to do is we're going to set up the problem as if it were in statistical mechanics in physics, where you have something called a version space volume, which is basically, I'm going to have some measure of the error. We call it either the microcanonical or the canonical measure, which is a measure of the error. In this case, an example would be, how different is the student from the teacher? And then you integrate over all possible students. And this gives you something called the version space volume. And the idea is we want to evaluate this volume. And this volume is going to allow us to estimate the error of a general purpose neural network. So what I'm going to present is a matrix. This is an old model. There's many, many papers on it. What I'm going to present, and we're writing up now, is a matrix generalization of this. So the idea, instead of having a perceptron vector, you have a matrix. And you have to use some techniques from random matrix theory and fairly advanced techniques, which actually come from quantum field theory, to evaluate these intervals.
Hey, Charles.
Yes.
I have a question which I was thinking of asking at the end, but maybe if I ask it now,
okay, go right ahead.
Prevent any confusion. So how are the teacher and student tied together in this model? Are you weighting this integral by like some notion of how similar the teacher and student are doing? Are you restricting it to only students that emulate the teacher on the data set? Or
what we're going to do is restrict the student to have the same spectral density as the teacher. So we've observed empirically that when you train large neural network, if you look at the weight matrices of very, very large neural networks, they all seem to be heavy-tailed. And throughout the formulation, as we work through the formulation, it won't be clear in this talk, but what effectively happens is that the students have to look like the teacher in some way. And in our theory, we're going to restrict the students to that the weight matrices of the students live in the same universality class of the weight matrices of the teacher. And so we have a paper. Go ahead.
This doesn't respect the actual label data at all so far. So for any given student with a set of weights that's in your set, a permuted version of the same student, which is sort of shuffling the input features, would also be in the set.
Yes, and we have to integrate over that permutation. And so the use of random matrix theory allows you to, the idea you're going to basically integrate over all those permutations in a way that they're invariant. But the main idea is, we have a paper in JMLR where we talk about these different universality classes. And the main idea is that the students live in the same universality class. In fact, it's the correlation matrix of the students that lives in the universality class of the teacher. And by selecting the students to have the same, generally the same exponent as the teacher, we're able to derive our alpha hat metric. And I'll try to show that. So let me kind of give you the idea. Usually what you would do in this theory is you would average over all the data and you would average over all the possible teachers. And you'd end up with this sort of double average. And it sort of looks like this expansion where you have a delta function, which is you have to restrict the student matrices to be so that they match the label. And this is just some technical thing that arises how you do quantum field theory, just these field theory integrals. But the basic idea is you get this sort of double average. And in order to formulate this theory, what I'm going to do is sort of fix the teacher. So we're going to fix the teacher to be the thing the model you've observed. So we have like, VGG19 or GPT-2, we've actually done this, these different models. And the idea being we fix the teacher, and we're going to just kind of, and we're going to average over all the students given that they're coupled to the teacher in some way. So though the idea is that there's some overlap between the student and the teacher. And this is an old model. This stuff actually used to be published in NIPS. I don't think I could ever get this published there now. But the idea is that there's some overlap. There's some vector overlap between the teacher and the student. R is 1/n j.t, where these are vectors. And the idea is that in the traditional student-teacher model, the error of the perceptron is basically an average over all the random teachers as you with this fixed overlap. So you integrate over all the students that overlap with the teacher, and then you integrate over all R. And so you get the sort of integrals that look like this. And this is sort of the key idea, is we're going to take this old model from this old idea of looking at the student-teacher overlap, and we're going to generalize this from a dot product to a matrix trace. So you end up with something like this. In the new model, in this matrix generalized model, we're going to have the matrices are heavy-tailed correlation matrices. We've observed that in most deep learning systems, we observe that W is not heavy-tailed, but the correlation matrices are, and we can characterize these correlations usually by fitting them to a power law or truncated power law. We've shown this empirically over hundreds of models. So we call X the correlation matrix of the teacher. A is the correlation matrix of the student. We say that the students are strongly correlated, and we want A and X to be similar. So we're going to integrate over all A that are similar to the X that we've measured. And we're going to use this sort of measure, which is this, we're going to move from the microcanonical measure to a canonical measure. So we're going to form this integral, omega of B, which is our version space, which is integral over all students, multiplied by X, EXP to the minus beta trace J transpose T, J transpose dot T squared. So this is the basic integral we're going to evaluate. And our claim is that evaluating this integral or something like it is going to give us an estimate of the generalization error. Now, we're looking at trends in the error, right? So we're not going to get an exact expression for the error. Our goal is to look at the trends in the error. So we're going to take two models and vary the hyperparameters or vary the depth, and we're going to get an expression which shows that we can represent those trends. So again, the idea is that this looks like a version space volume, where this is you're integrating over all the students. This term psi represents the error between the students and the teacher. We're going to look at a mean squared error. So we just look at the mean squared error between what the student would guess and what the teacher would guess. And this gives rise to this expression. This you can show to be, if you assume Gaussian data, you get an expression. You actually can get an expression exactly which has the overlap in it. I have to go a little faster. You work through these double integrals. I will skip some of this field theory stuff, and you end up with this sort of integral, which looks like this, which has two parts. One part which depends on the number of parameters, the size of the data set, and one part which just depends on this integral. This integral on the right is called an HCIZ or Itzhak-Zuber integral. It arises in quantum field theory and modern random matrix theory. And the goal is to evaluate this integral. And since I have 30 seconds, I'll go quickly. So this integral can be evaluated. You get a result which looks like this, where we're going to now average with a little algebra. You end up, instead of averaging over J, you average over the correlation matrices A, and you get an expression which looks like 1/n log in the large N limit of the expected value over all the student correlation matrices times this error function. This error function can be evaluated by a paper by Tanaka, which gives you a sum of what I would call generalized norms. And when you plug in the value for the eigenvalues of the teacher, you end up with an expression looks like z to the minus alpha for this heavy-tailed universality class. And when you plug so by assuming that the students have the same structure as the teacher and they live in this heavy-tailed universality class, you can write down an exact expression for our alpha hat weight watcher metric. So I think that's 30 seconds. I kind of had to jam it in there, but this is basically the idea, that you end up evaluating this expression for the error, this expected value in the large N limit, which is sort of a sum of what I would call generalized norms. And because we observe empirically that the weight matrices are heavy-tailed, we know what the form of this function looks like from generalized heavy-tailed random matrix theory. And that's what allows us to derive our weight watcher alpha hat metric. And I don't want to take the whole, so I'll stop there and just leave it for questions.
Yeah, that's really interesting that this metric comes from a place rather than just being empirically kind of derived.
Yeah, I've known this for some time, but how do I
Hmm.
explain it to people, right? It's not an easy paper to write.
So we should probably move on to the next person. But thanks for presenting this.
Thank
If
you.
you have
And
more
thanks for the
questions,
questions.
if you have more questions for Charles, he'll be in room number 1 with his name labeled in Discord afterward.
Yeah, let's move on to, thanks, Charles. Let's move on to Ganta.
All right. Thanks for setting this up. I really appreciate it. This is my first time here, so I hope that I will try to cover as much as I can about our work. Although there's a lot of slides, there's 40. I'll try to uh, focus on the more important one. So, hi everyone. My name is Diganta. I'm a master's student at Miller Montreal and also a researcher at Morgan Stanley. Uh, Today, I'll be presenting our work called as App Anytime Progressive Pruning. It's a collaborative effort with folks from Miller, Landscape, IIT Delhi, and University of Texas, Austin. Cool. Let's get started. So this talk will be divided into a few different sections. We'll have what's the motivation of the problem that we're trying to solve, followed by the design and algorithm that we are using to solve that problem, and some empirical analysis with some further open research questions. So the motivation is based on 3 different domains in deep learning, which are quite popular themselves. One of them, which is arguably the most important motivation for this work, is pruning. If you have been familiar with lottery ticket hypothesis or sparse neural networks in general, this should sound very familiar to you. So ideally, pruning, quote unquote, is just the process of reducing parametric complexity in a deep neural network where you remove redundant weights, where the definition of redundant can be followed by some heuristic. For example, in magnitude-based pruning, you usually remove the weights which have lower magnitude than a predefined threshold. And there are quite a lot of these works. In fact, Rosen also has a lot of interesting works on lottery tickets, which I have been quite inspired by. So I definitely recommend checking them out. Another very important component of this work is this new framework that Meta and Miller proposed last year in a preprint called as ALMA, which stands for Anytime Learning at Macro Scale. So if you're familiar with anytime learning, it can be very similar to an online learning setting, except in an anytime learning setting, your goal is to have a model where it is given a stream of data online, and the goal is at every point of training, you should have a good learner. So you're not only concerned with the final accuracy, but rather the integration of final accuracy at every point of the training. So as the author of the paper, Alma Kut, a good anytime learner should be one that produces high accuracy, can make non-trivial predictions at any point in time, and limit obviously the computational and memory resources that is used by the model. So if you look at the figure 1 that is showed on the slide, ideally what the paper Alma does is to try to estimate good wait times. So wait times is basically the time you should wait to collect a particular number of samples, which they call as a mega batch, to train iteratively on before receiving the next mega batch. So as you can see in that plot, the usual case where you do supervised training is the magenta line, where across the time you just keep collecting data, but you don't train the model. And at the end, when you have all the data collected, you train the model in a single go, and that causes the sharp drop in error rate. Which is called the tardy large scale learning, while in greedy learning, which is the blue line, is the classical pure online setting where you'll be learning on each new sample or each new batch of data that you're receiving at every point of time. However, in Alma, basically you're concerned with finding this optimal wait time that you should be waiting to collect each mega batch so that you minimize your total error rate over all the mega batches in the stream. And one loose motivation for this work is active learning. I understand that this domain has been sort of fading over the years because of the prominence in unsupervised learning. But generally in active learning, the motivation is that you have some budget or constraint that you have to respect. Especially the classical active learning scenario has associated label budget. So you cannot arbitrarily obtain n number of samples labeled, but you rather have n number of unlabeled samples, and from that you can only label a particular set of samples given that budget, and then you have to find which samples you should ideally label. And there are several methods that do this. So based on the motivation, this is primarily the question that we are trying to answer, is that given a dense neural network and a target sparsity, what should be the optimal way of pruning the model in ALMA settings? So in the original ALMA paper, the authors proposed progressive growing of the architecture when you keep receiving new mega batches, so as to accommodate the new information that is being received. But we are trying to tackle the opposite problem, which is to make the model smaller, and we have a given target sparsity that we have to respect. So by the end of the stream, we have a model that is basically pruned to that target sparsity. And our answer to that question is the framework that we are proposing, which is called as anytime progressive pruning. So let's take a look at the design of the framework. This might look a bit complicated, but let me try to break it down. I have an algorithmic version of this, which I'll share after this. But what is happening here is that given a dense randomly initialized neural network f theta, and we have, as I said, n number of mega batches in your stream. At each mega batch, we first take 20% of the samples from that mega batch randomly at the first iteration, and we pass the network and that set of 20% samples to at initialization pruner, which in this case is SNP, and then we prune the model to a percentage of that target sparsity that we have to reach by the end of all mega batches training. So let's say your target sparsity is 80% and you have total 8 mega batches. So at each mega batch, we'll prune by the model progressively by 10%. And what we further do is, once we have received this model from the pruner, which is pruned by that partial percentage, we'll then retrain or quote unquote fine tune it on that full mega batch. And then when we go to the next mega batch, we'll repeat the same process. However, this time we'll concatenate the previous mega batch data to the current mega batch data, which in classical continual learning is just using full replay, and repeat the same process. So this is how the algorithmic process look like. It's the same as I explained in the previous one, so I won't spend more time on this, but it's very important to note that we have this full replay on by default, and we always use SNP as the default pruning algorithm, and the SNP set that we are passing, which is the 20% random selected samples, is always 20%, and we are passing 20% of the full mega batch data, which includes the replay concatenated data as well. Okay, so before I go into more empirical analysis, I'll just summarize what our contributions are. So first, we obviously provide a comprehensive study into pruning in anytime learning framework, more specifically in ALMA framework. We propose this new framework of learning or sparsifying a model, which we call as anytime progressive pruning. And we investigate some very interesting training dynamics as compared to other baselines that we'll get into. And there's some interesting results that we still are working on to empirically ground. And further, we'll understand the effect of different pruners and do some application study. Some very basic TLDR, the mod operator always denotes the size, and the last point is the most important, is the 0.8 to the power tau into 100% represents the fraction of weights that is left after we have pruned, rather than the fraction of weights that are pruned. So whenever I say 36% sparse, that means that the model has remaining 36% weights as compared to the original baseline. In the work, we use two primary baseline. One is the default baseline that is used, which involves no pruning. It is just a standard model at full capacity, trained using stochastic gradient descent throughout all mega batches. To just clarify the difference between online learning and like classical online learning and anytime learning at macro scale is in online learning, you see the sample once, while in ALMA, you are allowed to see the sample multiple times, like you can iterate over it. And the OSP is the one where we reach the target sparsity at the first mega batch itself and then just train it subsequently. We also use this cumulative error rate, that is the total misclassified number of samples across all the mega batches, and we have a held out test set for this. So I won't go into ablation, but let's go straight into results. The results.
Hey, Diganta, we're at 10 minutes. Would it be possible to just quickly kind of summarize what the results are, and then maybe people can ask you in the Discord more about it?
Yeah, absolutely. So so the results basically state that we get improved performance, lower CER, and massively lower generalization gaps. So all of these results are available, but I just want to quickly highlight this one little thing that I feel is very important. So we find very interesting generalization gap trends when we increase the number of megabatches size, which goes into this phase transition like plot where we start with underfitting regime and then overfitting, and then the phase transition happens. This is not well explained as of right now, but we can discuss this later in Discord. So yeah, I guess we are out of time, but that's it from me. Thank you for listening.
That's really cool work, Diganda. I have several questions that I will try to, I guess, delay till the Discord, but
Absolutely, please.
Interesting work.
Yeah, me too. Cool. Let's move on to Ender.
Yay, I'm so excited. Okay. So basically, federated learning is a way of training a model. Federated learning allows you to train a model while keeping the training data on edge devices. So data stays local, and training data is not sent to a central server. Federated learning is used in Siri, in Hey Siri. Federated learning is used in Android messages and the Gboard mobile keyboard. And so what I'm proposing is that we could actually speed up federated learning by using mutable torrents to send and receive model updates. In the original 2017 federated learning paper, the authors who introduced federated learning in the 2017 federated learning paper noted that communication is basically the bottleneck for training. Communication is the slowest part of training. Usually when we try to make federated learning faster, we focus on upload time, which is the time that it takes for edge devices to send gradient updates to the central server. But we can also focus on the time it takes for edge devices to receive model updates from the central server. So that's what I'm focusing on here, which is both upload and download time for model updates in the training process using a mutable torrent. So let's see what the training process would look like using a mutable torrent to send and receive model updates. So first, the server samples from a set of clients meeting eligibility requirements. For example, mobile phones, which are edge devices that store data locally and don't send data to a central server, might only check into the server if they are plugged in on an unmetered Wi-Fi connection and idle in order to avoid impacting the user of the device. This is something that I'm quoting from the Advances in Open Problems in Federated Learning paper that was last edited in 2021. These are the stages of federated learning. The second stage of the training process is broadcast. The selected clients download the current model weights and a training program from a mutable torrent. That's something that I'm proposing. So how is this helpful? Why would this be helpful? So this torrent would be a shared file that's saved on the client's file system. Traditionally in federated learning, edge devices need to communicate with a central server, and they spend time communicating over a Wi-Fi network. But with a mutable torrent, they don't need to communicate over Wi-Fi. They're communicating over a distributed hash table and saving and sending and receiving model updates over the torrent's distributed hash table. That's how they're sending and receiving model updates. Now, the question is that faster than Wi-Fi? My guess is that there's probably a point at which the model becomes so big that when models become big enough for this to actually be faster than Wi-Fi, and it might just be faster than Wi-Fi, period. But I definitely think that for large models, this is faster than Wi-Fi, because training large models with federated learning is an open problem. But this might also be useful for models that are not large. So that's an open question. Is this even fast? Client computation. So this is how we train the model. Each selected edge device locally computes an update to the model by executing the training program, which is probably going to be stochastic gradient descent, which is what we do in federated averaging. This is also from Advances in Open Problems in Federated Learning.
Sorry, Andrew, we can't hear you anymore.
Oh no, what's wrong?
Oh, now we can.
Oh, okay. What did you hear last?
At the moment you flip to this slide, I believe.
Okay, so am I okay?
Mm-hmm.
Okay, so during the aggregation phase, each edge device saves their model update to the torrent distributed hash table. And the idea is that communication is the slowest part of training a model using federated learning. And so if the torrent is already being seeded locally, we're not using Wi-Fi to send and receive model updates. We're using the torrent's distributed hash table. And this is how we're going to aggregate model updates in this proposed training process. Again, is this faster than Wi-Fi? That's the open question. Also, in this stage, this is usually where in traditional federated learning, this is where the stage in which we try to use secure aggregation to make sure that the model updates don't reveal anything about the edge devices that are taking part in the training process. But I haven't accounted for that in this proposed training process. And so that's something else to consider. And so then this is the model update stage. So one peer would compute the shared model based on the aggregated update computed from the clients that participated in the current round. And the shared model would become the content of the mutable torrent. So what's interesting is that with the mutable torrent, you're able to subscribe to elements in the torrent's distributed hash table that are of interest to you. And so you're able to subscribe to their public keys in mutable torrents. This is called the BitTorrent proposal 46. And whenever you get an update, the content of the torrent changes, but you're still seeding the same torrent. And so I think that this would reduce communication time. for the training process. But again, you know, this is just my idea. And that's all. I envy the people who had a lot more math. This is just more of a infrastructure idea than a mathematical formulation. So I'm open to questions.
So if one were to try out this idea, are there any like open sourced torrent setup out there that people can use? Do you know?
Oh, absolutely. If you look up mutable torrent on GitHub, there's a lot of implementations of mutable torrents, and you just need to use that to save model updates. The only issue is that those are usually written in JavaScript, and most machine learning code is written in Python. And so I was thinking about how to bridge those. I think that would be the messiest part.
I see. I don't know exactly how torrent works, but my understanding is that it allows both downloading and uploading at the same time to like efficiently use the bandwidth. And I was thinking, because in the current federated learning framework, even the ones that you proposed, downloading and uploading, or I think like aggregation and model update are still separate phases. Do you think there's a way to combine them to make use of the torrent setting?
Oh, that's really interesting. Combining downloading and uploading. I knew that there would be something I hadn't thought about in a question. I think that that's like actually the best part of this idea, because you can subscribe to public keys that are technically seeded. Like you can subscribe to a public key, right? But in this torrent proposal, even if you are asking for a public key that is basically, you ask for a public key from the distributed hash table, but you're still seeding other public keys. And so it could reduce the communication bandwidth of training for you to be able to download and seed multiple pieces of information at the same time that are not necessarily what you're asking for. And so what I'm trying to say is that I think it would be possible to combine those phases by trying to figure out how to compute things in the background maybe, but it's really hard for me to think out loud. I'm not a think out loud person, but I think that's a great question.
Yeah, I also don't know if that is a valid question at all. That was just my impression of torrent is that they do both things simultaneously, but I could be wrong. Cool, thanks. Any other questions? Okay, so for more questions, people can move on to Andrew's Discord room after this. Let's move on to Sai Ram, if you're ready.
Yeah. Hi, everyone. My name is Sai Ram. I'm a fifth-year PhD student. And in this short talk, I'd like to present an overview of what work my team and I together we've done. So I'll get started. In this work, we've proposed a data set for visual question answering. And for those who don't know what VQA is all about, VQA essentially studies the development of models, neural networks, in most cases, that take an input image and a text question about that image, and then the model returns an answer to the image. So for example, how many slices of pizza are there, or is this a vegetarian pizza? This is an actual image and couple of questions from the VQA data set. VQA largely concerns, most of VQA concerns with the development of models rather than the evaluation of models. So what we did was we first took a look at certain existing data sets for VQA, and we wanted to know how good they are in terms of what do they give a proper evaluation of the learning of models. So we thought there are like two broad classifications for data sets. One of them, one category is our natural image VQA data sets, such as the eponymous VQA data set, visual genome, and GQA, shown in order from left to right. And then there is the well-known clever data set, which consists of 3 classes of objects set and generated using Blender. And before I continue, because our data set is also a synthetic data set, I would like to just say why synthetic data sets for VQA why using synthetic data sets for VQA is actually a cool idea. For one, it gives us control. So you could train and test for certain specific concepts. So this is what the clever data set does in its cogent sub data set. They have 3 class of objects and around 10 to 15 objects, I think, uh, in an image. And only in the trained data set, only certain objects, say cones or cylinders, uh, say cubes, could be given only red, and then in the test data set, the cubes would be assigned some other color, say gold, or here, oh, this is not a good example, but some other color, and then you would want to evaluate if a model has understood the concept of that particular color. And this is what was done in the cogent subdata set of Clever. A related point here is using synthetic data sets could potentially give us a way of simplifying evaluation of certain concepts. And what we are interested is in the so-called compositional learning. What we mean by compositional learning here is learning a particular concept, learning to answer questions about a particular concept, even when the scene compositions change. For example, I want to understand the notion of rightness. Like what does it mean to have an object A right of an object B? One good test for it would be to have that A and B are in the relationship right of when A and B have never been in that relationship in the trained data set. That's a pretty strong test of compositional generalization. And this is what we are aiming for in our data set. So we identified that there are 2 properties of good VQA data sets. The first being complexity. You would want a reasonably complex data set so that you want to evaluate the model's expressivity, how rich is the class of functions that it can learn to approximate. And the second concept is that of separation. That is, we don't want common information between the train and the test data set. For VQA, we don't want common pairs of objects occurring together in both the train and test data set, as this would mean that we would have, usually this would mean that we would have common information between the train and test data set. And even worse, the even worse cases where you have not only objects that co-occur, but also objects that co-occur in the same relationship in the train and test data set. So we we just evaluated existing data sets, some of them based on both of these concepts, complexity and separation. And what's in bold is our data set with a boring name, unseen, uncommon objects in unseen configurations. We found out that the natural image data sets are reasonably complex, while Clever, the simple data set, the synthetic data set, was not really complex. It had only 3 classes. And as an in-between kind of data set between natural images and synthetic images, our data set UOUC is reasonably complex and, as we shall see, extremely separated. So what we did was, for every, we found out the average number of objects that co-occur in for a given test scene, the average number of objects that have co-occurred somewhere in the trained data set. And we found the numbers are pretty large for visual genome or for GQA. Both of these are very popular data sets. And the numbers look deceptively small for Clever Cogent, but that's because we have fewer number of objects in Cogent per scene. We also found the average number of relationships that occur between the same objects for a given test image common to the train and test data set. And we found these numbers are also non-zero. And UIUC, our data set, is constructed so that this number goes to 0, in that both the train and test data sets are very well separated. So very simplistic thing over here for existing data sets. The natural data sets are good in terms of complexity, but they're bad in terms of separation, whereas clever is bad in terms of both. And in our data set, so we handle complexity by using 380 classes of drawn from 528 characters from Dungeons and Dragons. As we shall see, these characters are far more complex than the simple geometric figures used in Clever. And at this point, I should thank Miguel Zavala, who is an independent guy who is just creating hundreds and thousands of these models. We have put a link to his page in our archive preprint. As I pointed out, these objects are quite complex, and that the train and test sets have no common co-occurrences. And as an aside, though we aren't covering this due to lack of time, the objects are given properties based on a classification of their type. Any person who's played D&D knows that there's a great potential for classifying objects based on varieties of categories in D&D. So these are some of the examples of the objects. So they look pretty cool, and just as a bit of a joke, I should have called it caves and creatures, like Dungeons and Dragons, but we came up with a boring name instead. These are example scenes that we have. I'm sorry, I didn't zoom it enough, but in our preprint, maybe this will be good motivation for you to take a look at our preprint. The objects are pretty complex. So yeah, we wanted to obviously a data set. Motivating a data sets based on its evaluation of models. So we took 4 models: MAC, LCGN, Mutan, and show, ask, attend, and answer. All of these models have non-random performance on either Clever or GQA or the 2 VQA data sets. In particular, we'd like to point out that MAC GN achieved close to 98 or 99% on Clever. That's pretty impressive. However, as deep learning progresses, we need better benchmarks. So, on our data set, we have 4 kinds of questions. First is evaluate for a model's understanding of spatial relations. This is actually the main challenge of our data set. We'd like to know if models can understand the concepts of leftness, rightness, frontness, or hindness between objects. Then we have, so we have 4 questions on this in the details right now. We have 2 questions on simple reasoning, essentially asking if a model could understand the concepts of comparing numbers and counting. We have a 1 single question relating to perception, just asking to recognize if object is there in a scene. And the last is just a sanity check for models based on asking a model if it could answer questions that aren't based on, and these are our results. So the first column is on binary questions, so like random, and we notice that all the models perform randomly. Symptoms easier for MAC and LCGN, which are the best performing models. Perception is by hands down the easiest task, and memory-based questions are understandably easier. But what's also interesting is 2 pretty decent baselines perform very poorly.
We should wrap up pretty soon if we can.
Yeah,
that'd be great.
Yeah, just 10 seconds. I'm in my last slide.
Perfect.
So the last 2 models perform pretty poorly, and we hypothesize that this could be because of the changing test distribution, since no objects co-occur in our train and test data sets. So there could be a lot of differences in the images. So lot of that I've missed. You could check out our work in our archive link. I'm open to questions.
Let's save our questions to Discord and instead move on to Stefan. You're here.
I'm going to start with, so I have two ideas to present today. I'm going to start with the second. This one's called Splytters, Adversarial Train Test Splits. It's in the very early stages. And if you listen to this and you think it's interesting, you want to contribute or want to get involved, just reach out. Okay. So we're all familiar with what a train test split is. We do such splitting in order to estimate model performance on unseen data. Typically, or at least like in a textbook fashion, this is done in a random fashion. We randomly separate a data set between, for instance, 80% training and then 20% testing. This can also be done in a k-fold fashion. Recent work, however, in particular, Sogard et al. 2021, titled "We Need to Talk About Random Splits." This appeared in EACL 2021 and it won an honorable mention as a short paper. It argued that random train test splits lead to overly optimistic performance estimates. Typically, this is due to what's called data twinning, where we see a high level of similarity or overlap between samples in a test set and a training set. The paper argues that multiple bias splits lead to more realistic performance estimates than multiple random splits. The emphasis here is on biased. What they mean by biased is what they introduce the terminology of as a adversarial split, where they intentionally construct a train test split in such a way that the training set is different somehow from the test set. The word different is a little bit vague, but it can be, there's a ton of different ways you can make it different enough. And the paper argues that doing adversarial train test splits may provide a better performance estimate for a model's ability to generalize. Examples of adversarial splits include pretty basic things like if you have an NLP data set, you can sort all your samples based on length and then just cut it somewhere in that sorted list, put all the shorter ones in training and all the longer ones in testing, or vice versa. A little bit more advanced would be using the Wasserstein distance in an embedding space so that you can maximize the distance between the training and testing data distributions. As a concrete hypothetical example, this is pretty trivial, but it gets the point across. Pretend that we're interested in something like text classification. This could be one intent for a intent classification data set, where all the queries in this intent or class are targeted towards asking about a bank balance. If we do this randomly, we might get a high degree of similarity between certain queries in the testing set and also the training set. So I've highlighted certain key features like balance. Notice this occurs in this testing sample. It also occurs in these two training samples. Not only that, but there's a almost exact duplicate. What is my balance? And my balance is what? So this is what an example of twinning is. Similarly, we have how much money appearing in both this query and then this one in the training set. So our model would learn, okay, balance and also how much money. When it sees these in the test set, it's pretty much already seen that at training time. So it's going to have an easy time at these test samples. Alternatively, what we can do is construct an adversarial split of our data set where we use some measure of difference or distance or dissimilarity to somehow separate or group the data so that we've got all these similar instances in training, and then these ones in testing. So what we would be testing here is a model's ability to learn from these examples where we only see balance. Then the model would have to, if it's good, it would have to know that, okay, balance means, it also means how much money do I have. So this would be a more rigorous test than if we split the data randomly like this, where we might have this twinning artifact. And so the idea that I present today is called Splytters. It's just an idea to extend the work by Sogard et al. 2021 to introduce maybe a library of various adversarial splitting functions, a Python library for doing that, that could facilitate a wide variety of what I call model independent adversarial splits. So these are basically just looking at the data and splitting solely based on the data, as opposed to having like a model in the loop where we might analyze the loss function and incorporate that. That could be done later or something. And the end goal here would be to use this library of adversarial splitters to analyze various models and tasks in NLP and computer vision. I haven't really thought about tabular data. I know Bernice mentioned tabular data and evaluation. I think this type of library could be used on tabular data as well, assuming the tabular data could be basically put in an embedding space, and then you can do all these distance functions in that embedding space. So if you're interested, feel free to stop by the half-hour Discord later. I also put my email on the front of these slides, so you can reach out there. Jason, how many minutes do I have?
You're at 7, so I guess
okay.
3 more.
I think I'll end it there. Rosanna, I apologize for signing up for 2 and only doing 1.
You submitted 3.
I submitted 3, narrowed it down to 2.
So many ideas.
Ended up doing 1.
Yeah,
Time flies when you're having fun, though. So.
Yeah, we can save it to next time.
Okay.
But thank you for submitting 3 ideas. I was so surprised when I saw the submission. I do like this idea. I mean, an easy thing you can do is you create a adversarial split of all canonical data sets and then just evaluate all the SOTA models on it and have a paper that says, oh, all of them drop 20% just by using a different split. I wonder if you thought about using a trained model to construct the split. So basically you pick out the samples in the test, or even in the train that are creating large errors, collect them, retrain the whole model, using the gradient information that's already present in training.
Yeah, that is definitely a valid way of doing it. That would be the more model dependent method. I think in the feature selection field, they call it filter versus wrapper, right? I think I want to start with the filter approach where it's just data dependent. I think the model dependent approach probably would yield interesting results as well. And I eventually want to get there, but.
So question, in what scenarios do you think that this approach would work well? And in contrast, in what scenarios would this approach work poorly, but an approach where you did use the model or a model would work better? Like, how should we think about these 2 different worlds?
I mean, one risk of using the model could be you have a bad model or something. I don't know. I'm not too sure what the answer to that would be yet.
I guess I'm thinking the examples you showed on NLP, where you were kind of figuring out which train test splits to use based on just the frequency of individual words. That's the sort of thing that you can kind of assess just on an input data level, versus maybe for image processing, computer vision, you might, if you just look at each pixel separately, you're going to find a lot of red and green pixels in many images. Rather, you would need to put it through a model and look at co-occurrence of certain higher level features to really come up with a meaningful train test split.
Right. Yeah. For images, one typical way of doing it could be like use clip or some ImageNet model to embed the image, and then you do the similarity computations in that space. So in that sense, it wouldn't be totally data dependent and model independent. There would need to be a model for embedding the image into the vector space. That could also be true for a text, like using a BERT model for encoding the text into a vector space. Yeah.
I guess you could use your same library. Once you write your library, you could use the exact same library, but just on the embedding space, right?
Yeah, so the initial idea is basically to have this as a library that operates on just vectors. It doesn't matter how they got there, as long as they're vectorized, then you can use it.
Cool.
Going
I'm
further,
happy
we
to
want
chat
to
on
analyze
Discord.
which.
Oh, sorry, go ahead. I just want to say, yeah, I love adversarial test sets and adversarial splits. I think they're really interesting. I'm really happy someone shared the dichotomous data difficulty paper, because I do think this like model-based difficulty thing works. But maybe to go to Jason's question, I mean, there are metrics that have some sense of that are, attempting to kind of estimate difficulty of a example or out of distribution examples.
Mhm.
That might be one for the model independent approach.
That's all I have. Thank you, everyone.
Cool. Should we move on to Discord?
Yeah, maybe we can give a round of thanks for all the speakers,
Thank you.
virtual or otherwise.
Cool. Let's move on to Discord. Do everyone know our Discord server link? I can paste here.
Quick question. I think I'm in the Discord, but I don't see oh, now I see the channels. I lied. Okay. Thank you.
Yeah, we have a lot of channels. So there's a category called Research Jam, and then if you go into it, there are 5 people's names.
Perfect.
Okay, see you there. Thanks for joining, everyone.
Thanks again for doing this.
Cool. Bye.